Have you ever looked up at the sky on a beautiful day and wondered, why is the sky blue? Well, today we're going to show you. It all starts with the sun. Energy from the sun is coming down to Earth in what are called electromagnetic waves. We can feel it as warmth and see it as light. There's also energy that we don't see, like radio waves, gamma rays, and UV rays, which can give us sunburns. Photons are the particles that bring the energy down to Earth. They move in a wave, like the waves in the ocean. But electromagnetic radiation doesn't all have the same energy, so there are lots of different waves that make up sunlight all jumbled together. Here's another way to think of it. Imagine two balls, one blue and one red, released together that reach you at the same time. The blue ball bounces more often than the red ball, but both cover the same distance in the same amount of time. The frequency that the blue ball bounces is higher than the red ball. It seems more energetic. Now, frequency is also related to wavelength. Wavelength is the distance between the tops of the wave, or in this case, the top of each bounce. As you can see, the blue ball has a shorter wavelength than the red ball. So the higher the frequency, the lower the wavelength, and vice versa. Photons, since they're particles that move in waves, also have a wavelength depending on how much energy it has. Sometimes the wavelength is long when there isn't a lot of energy, and sometimes it's small when there's a lot of energy. Our eyes can't detect really short wavelengths like gamma rays and X-rays, and we also can't see really big wavelengths like radio waves and microwaves. But what we can see is called visible light, and our eyes have the ability to distinguish higher and lower wavelengths that fall within this range. The energy that comes from the sun is all mixed up. When all the colors are together, we see it as white light. But if you put the light through a prism, it gets split into its different wavelengths. We see these different wavelengths as different colors. Shorter wavelengths, which have more energy, are violet and blue. Longer wavelengths are orange and red. The light waves that come from the sun travel in a straight line unless something gets in its way. Then it does one of several things. For example, it might be reflected, like if it hits a mirror. It might bend, like with a prism, or if it gets in contact with small particles, it will scatter. And for almost all matter that it comes in contact with, it'll lose a little bit of energy through absorption. For example, think of a blacktop that gets hot on a summer's day. The reason why the sky is blue has to do with how sunlight interacts with air. Air is made up of gases like nitrogen, oxygen, argon, and carbon dioxide, and each one of these particles is a tiny molecule up in the atmosphere. As light waves travel through the air, they come into contact with these molecules and they start to scatter. But the interesting thing is how well a wave is scattered depends on its wavelength. That means blue light and red light don't scatter with the same frequency. It turns out that lower wavelengths, meaning higher energy photons, scatter way more than high wavelengths. This process is called Rayleigh scattering. And how well or how much it scatters can be thought of its intensity. And as it turns out, a wave's scattering intensity is inversely proportional to the fourth power of its wavelength. There's actually a fancy equation that calculates the intensity using wavelength, particle diameter, refractive index, and distance, but don't worry, we won't test you on this. Just know that smaller wavelengths scatter more, which means more blue light will scatter than red light. And when blue light scatters, it's sent down to our eyeballs, and that's why we see blue. But wait, why is it that when the sun starts to set, we start seeing more yellows and oranges and reds? There are several factors that make the sky turn red during the sunset. One major factor is that the longer wavelength light waves are now able to directly reach the viewer. Also, because the sun is lower in the sky, there's more atmosphere that sunlight has to travel through before it reaches us. Blue light continues to get scattered as it travels through the air molecules, bouncing away and sometimes getting absorbed by obstacles it meets. This allows the reds and yellows to pass through and finally reach us. One final thought. Remember when I said different wavelengths scatter with different intensities? Part of that fancy equation also takes into account what particle the wave is hitting. That means that if the atmosphere were different, light would scatter differently. And you know where the atmosphere is different? Mars. Where ours is mostly nitrogen and oxygen, Mars is almost all carbon dioxide. And that means light scatters differently on the surface of Mars. So if you were there and looked up at the sky, it wouldn't be blue, it would be red. I guess that's why they call it the red planet. And do you know what this world-famous photo is called? The blue marble. So now you know. The next time someone looks up and admires the pretty blue sky, you can tell them to thank Rayleigh scattering. Thanks for watching. We'll see you next time.